Hey everyone, on this lecture we are going to implement hill climbing for a constraint satisfaction problem in artificial intelligence and operations research. Constraint satisfaction is the process of finding a solution through a set of constraints that impose conditions that the variables must satisfy. The constraint satisfaction problem that we are going to solve using hill climbing is the n queens problem, where the goal is to place n queens in a n times n chessboard, such that no two queens threaten each other. So remember, in a chessboard, queens can threaten each other if they are present in the same row, column, or diagonal on the chessboard. Remember, one of the applications of hill climbing was to use it for constraint satisfaction problems. So let's begin with the implementation. So we open our code environment. In this case, we have Visual Studio to implement C++ language. So in the previous lecture, we implemented hill climbing for a function optimization problem. Hill climbing has many applications. The two most common ones are for function optimization and constraint satisfaction problems. So let's begin by including the input and output library, the IO stream. We also include the vector library because we are going to work with vectors to represent this chessboard. Finally, as we did on the previous lecture, we are going to include the random library of C++ to generate these random numbers, that they are pseudo-random numbers. Okay, so let's begin by defining the main program. Okay, from this main program we are going to define the functions that we are going to call, and then we're going to define them here above. So first of all, we need to indicate the number of queens that we want to place. Of course, this number n is going to also define the dimensions of how many rows and how many columns we will have in the chessboard. Always is going to be a square chessboard. So we define the n, for instance, to be 8. This is the number of queens that we want to place in. And then we can also define the maximum number of iterations that we are going to use in hill climbing. And also remember from the previous lecture we showed that hill climbing had two main parameters, the step size and the maximum iterations. However, for this case, for this constraint satisfaction problem, the step size is not specified, neither used, because the algorithm operates on a discrete search space. Each iteration of the algorithm is going to work by exploring a neighboring solution and by moving one queen to a different row within each column. So the step size is not used. The step size parameter is used in continuous optimization problems where the search space is continuous, as we did on the previous lecture. So here let's define the maximum amount of iterations to be 800, for instance. Now remember that hill climbing works by beginning with an initial solution, evaluating this solution with the objective function or a evaluation metric, and then exploring neighboring solutions if we find better ones. So here the initial solution, or the initial state that we can set, let's define here a vector of integers. Okay, let's call this initial state. And what does this represent? The size of this vector is going to be n, and this vector represents the sequence, okay, for the queens. For instance, imagine if we have something like this: 2, 7, 1, 4, 5, 8, 3, 0. Imagine that we have this. This solution, or this vector, okay, imagine that this is the vector that we have. What this is saying is that the queen in the first column is placed at the row 2. The queen in the second column is placed at row 7. The queen in the third column is placed at row 1. Okay, and so on. So this is what is representing. Each number corresponds to the row position of a queen in each column of the chessboard. And so since we represent indices from 0, okay, beginning from 0, so this is going to be the column 0, the first column is going to be the column 0. Okay, so in the column 0 we are going to place the queen at row 2. In the column 1 we are going to place the queen at row 7, in the column 2, okay, and so on, because we always begin with array indices from 0. Very important to know how to interpret this vector. Also here let's define the using namespace std in order to avoid explicitly defining the std whenever we want to use the standard library. And so we need an initial solution. What this initial solution could be? Well, for instance, we can define a very simple and naive solution at the very beginning. We can do a for loop in here. And so we can set the value of the vector initial state at position I to be precisely equal to I. In that case, we are going to have at the column 0, I'm going to place the queen at row 0. At the column 2, or in this case, at the column 1, I'm going to place the queen at row 1, and so on. Of course, this is not going to give us the optimal solution. However, this is the beginning solution, the initial state where hill climbing is going to begin from. So here we are going to solve the n queens problem using hill climbing. And the way to do this, we can define the vector solution. And so this vector solution is going to be the application of the hill climbing algorithm. Remember, on the hill climbing, we need an initial state, and the parameters. In this case, the only parameter that we have, since we have a discrete search space, is the max iterations. Okay, so this solution, this algorithm is going to return precisely the solution in the same format as the solution states. All of the solution states need to be defined in the same format, right? So essentially, if we have something like this, 4, 6, 1, 3, 0, and so on, this is saying in the solution that the column 0 at the first column of the chessboard, the queen is going to place at row 4. At the column 1, the second column of the chessboard, the queen is going to place at row 6, and so on. Very well, so now let's implement the hill climbing algorithm. So here, since this hill climbing needs to return a vector of integers, here we need to define this a vector of integers. The name of this algorithm is hill climbing. It is going to receive an initial state, okay. Also here the parameter that we pass is this initial state, like this, right? So this initial state that we are going to pass is going to be a constant initial vector. We are not going to modify the initial state. Therefore, we can pass this with a const, okay, keyword. This basically means that we are not going to modify this vector, it is going to remain constant. And then we pass this vector, vector int. And here, the name, we can put any name for the parameter, let's just say initial state, okay, to have the same name. Although this is not mandatory, but what is very important is that we pass this vector by reference. Parameters in C++ can be passed by value, okay, by copy, or by reference, where we pass actually a pointer to the memory reference where this variable is allocated. In this case, this vector. Passing vectors by value or by copy is very inefficient, okay, and degrade the performance of our application. We always need to pass all vectors by reference, and we can do this with this & symbol. Right? With this, we are passing the vector by reference, which is much more efficient. And here we pass the attribute of the maximum iterations. Okay, so let's begin implementing the algorithm. Remember, we begin with a current solution or a current state. This is going to be initially equal to the initial state. So here we can define the current state should be equal to the initial state at the very beginning. And now from this current state that we have, we need a way, an evaluation metric to see how good this state is. And the way to do this in this problem is basically by computing how many queens are threatening each other. Of course, ideally we want this to be 0. This is how we solve this problem, right? So let's define this evaluation metric, okay, or we can call this function calculate conflicts. So here the current conflicts that we are going to have is going to be the application of the function calculate conflicts in this current state. So now let's implement this function that calculates the conflicts of how many queens are threatening each other. This is going to be a function that returns an integer. Okay, it is going to return the discrete value, natural number. How many? Okay, a counter. So it is going to receive a state. This is going to be a constant state. Okay, a sequence of queens in each column. So this is going to be the state. And so now what happens? Well, we know for sure that each queen will be placed in a different column by the definition of the format of these solutions. Each state is represented by a vector, a sequence of queens. Each value of this vector is the position of the row, and each position of the vector is the position of the column. So we know for sure that the column will always be the queens are always going to be placed in different columns. So we only need to ensure the condition and verify how many queens are placed in the same row and in the same diagonal. Let's begin by defining the number of conflicts to be initially equal to 0. we define the size of the vector to traverse. So the size of this state is how many columns we have. So this is state size. With this we can get how many numbers we have in this sequence, how many columns. Very well. So here let's traverse all of the sequence. So this I variable is going to traverse the elements of the sequence, of the columns. Here we can increment the I, and then we are going to have another loop to traverse the following columns. So here for int j is equal to I plus 1, j is less than the size, we increment j. And now what we need to do here, we need to check for row conflicts. So we check for row conflicts and diagonal conflicts. To check for row conflicts is very simple. We don't need to check if the value of the row at this given column is equal to the value, okay, or the value of the row is the same row of this other column j. Know that this loop is going to traverse to all of the elements of the sequence. Imagine that I have this sequence 2, 5, 1, 0, 7, 6, okay, 4, okay, we have here until 3. Imagine we have the case for n equal to 8. So this for loop in here is going to traverse all of these elements, and then this for loop in here also is going to traverse all of the elements, but for all elements that come after a given one. So let's begin. First case, I is equal to 0, we are here. Then we traverse all of the cases for elements different to this one. So we traverse this one, and we compare with this one. We traverse this one, we compare with this one. We traverse this one, and we compare with this one, and so on. Okay. Once we have compared 2 with all of the rest, we now increment I. So now we got to the position 1. And we basically apply the j loop, the inner loop, for all of the elements different from I that come after. So we compare 5, okay, with 1, 5 with 0. Okay, and here some people may say, why you're not comparing 5 with 2? Well, we already compared this before, right? When we were analyzing the case of I equal to 0, we were the case where we were here, and we already compare 5 with 2. We don't need to compare once again. This will not be efficient. Once we have already compared a given pair, we are not going to compare it anymore. So we compare 5 with all of the rest. Then we compare 1 with all of the rest, and so on. This is what we do in these two loops, in the outer loop and in the inner loop. With this, we check if they have the same role. So we have a conflict. And how can we check the diagonal conflicts? Well, we can define and formalize a diagonal conflict. First of all, let's formalize what is a conflict. A conflict happens if there is a row conflict or if there is a diagonal conflict. And a diagonal conflict takes place when the absolute value, okay, of the subtraction of the row at this column I minus this row at this column j. Note that we compute the absolute value, so we always have a positive value at the end in here. If the absolute value of this is equal to the absolute value of the column I minus the column j, okay, this means precisely that we have a diagonal conflict. And to visualize this is very simple. Just suppose that we have just this chessboard. Imagine that we have here size of n equal to 4, right? 4 times 4 chessboard. And here we have, of course, we can see clearly, okay, here we have a diagonal conflict, right? But as the formalization goes in the code, what is happening here? What is happening here is precisely if we subtract, okay, this specific, in this case, the diagonal conflict is going to be happened if we place this one in here and this one in here, right? This is the formalization. So as we can see, we have a conflict in here. This is very simple to see in the visualization if we put the chessboard. But analytically, it is also very simple to check. Keep in mind, if we subtract this row, which is the row where we place this queen, and this row, which is the row that we place this queen, this gives us 2, right? In the same way, if we subtract this row and this row, 3 minus 1, also this gives us 2. So the subtraction, the absolute value of the subtraction of the rows is equal to the absolute value of the subtraction of the columns. Therefore, we have a conflict. Okay, this is the way to verify that we have a conflict. The same way we can check in this case. What if we put an element in here and an element in here? Okay, just imagine the element in here. Do we have a diagonal conflict? Of course. Okay, of course, because if we subtract the rows, okay, let's subtract 0 minus 1. This gives us equal 0 minus 1 is equal to 1 in the absolute value. And if we subtract this 2 minus 1, the absolute value also gives us 2. So we have a conflict because the subtraction gave us the same, right? So this is the way how we check if there are diagonal conflicts in the analytical way. And this is precisely what we're doing in this expression in the code. Right? We check if there is a conflict diagonally. So if this happens, if we have either a row conflict or a diagonal conflict, we are going to increment the counter of conflicts. So this will mean that both queens, okay, are threatening each other. The queen at column I and the queen at column J. Okay, so with this we are done. Finally, we can return the number of threatens or the number of conflicts. We return here the number of conflicts that we have found given this particular state, given this particular solution given. So now once we calculate the number of conflicts in the current state, then what we do is we begin the main loop of the hill climbing. Remember, the hill climbing, this is an iterative algorithm, so we are going to execute this max iteration times. Now, in the main loop, what we do, remember from the previous lecture, is the same structure, is the same code structure. We need to generate a neighbor. In this case, what is going to be the type of neighbor? Neighbor is going to have a type of vector. It's going to be a sequence, an ordered sequence in the solution sequence of the queens placed, right? So here we're going to just say here neighbor. This is going to be equal to the generation of a random neighbor. So we are going to implement a new function, generate random neighbor from the current state, right? And now, since the search space here is a discrete search space, the way to generate the neighbors is not going by adding a step size, okay, in a particular range, okay, normalized range of the step size as we did on the previous lecture and the previous implementation. Now we are going to do it in a different way. So before continuing with the main loop, let's now define this function generate random neighbor. We can define it in here, for instance. So this is going to be a function that is going to return a vector. The name of this function is generate random neighbor, and it receives a state, a solution, which is going to be a constant vector int state. So first of all, what we do is we need to create a random number generator device. It is used to obtain random seed for the random number engine. We can declare with the random device. Let's name here RD. Now we need to create a random number engine, and this can be done with the Mersenne Twister random number engine. If we type MT19937, we call this gen, and we seed it with a random value obtained from the RD, the random device. Here we just type RD. Now we need to create a uniform integer distribution that produces random integers between the value 0 and the size of the chessboard, right, -1. Because if the size of the chessboard is 8, we are going to have indices from 0 to 7. We can do this with the uniform int distribution. We can call this variable distribution with this. This is going to be from 0 to the state size -1. And remember, whenever we define a new uniform int distribution, we need to define this between the symbols less than and greater than. So remember, the objective of this function is to return the neighbor. So initially, let's define the neighbor to be equal to the beginning state that we're given. So initially, the neighbor is going to be equal to this state. And now we are going to declare two indices that are going to be between 0 and state -1. So we are going to apply the uniform distribution method with this generation. This is the seed that we have, and we do the same with the index 2. Okay, we generate a random value with this seed inside this distribution in here. So we are going to have here values from 0 to 7, and also here values from 0 to 7. Remember that the value of n is 8, therefore the size of this state solution is also n. Very well, so once we have the indices, the way to generate the neighbor is very simple. We don't need to swap the value of the row of the neighbor at the column index 1 with the value of the row of the neighbor at the column index 2. Imagine if we have a solution like this. Imagine that the index, okay, that we have index 1 is equal to 2 and the index 2 is equal to 0. In that case, what we are going to do, we are going to swap the index 1, which is here the column 2, so 0, 1, 2. We are going to swap this 5 with the column 0, which is the index 2, with this 2 in here, right? So what is going to happen is we're going to have something like this: 5, 9, 2, 4, 1, 3, and so on. This is what we do with this swap. We are swapping these two values of the rows for these given columns. And at the end, we return the neighbor. So with this, we can just return the neighbor. Very well. So with this, we can generate random neighbors in this discrete search space. So now in the hill climbing algorithm, once we have the neighbor, what we need to do? Once we have the neighbor, we need to compute how many conflicts we have in this neighbor so that we can check if we have a better solution or a worse solution or the same type of quality solution. So here we define a variable neighbor conflicts. This is going to be the application of conflicts calculation, and this we are going to pass this given neighbor that we have just computed. And now we check inside this same loop, we check if the neighbor conflicts that we have just generated is less than the current conflicts that we have. Then we set the current state to be equal to the neighbor and the current conflicts to be equal to the neighbor conflicts. That is, we update the solution. We have found a better solution. Okay, so here we find a better solution. And this process is going to be done iteratively until the end of the hill climbing algorithm. Okay, once we have performed the number specified of iterations. And so at the end, what we are going to do, we are going to return the current state, which is the current solution that we have. Okay, at this moment, at the moment of finishing the hill climbing, all of the hill climbing iterations. So at the moment of finishing the hill climbing algorithm, this is the optimal solution. So we just here return the current state. Very well, with this we have ready the hill climbing algorithm. We can test this algorithm in the main program. Now once we have the solution, we can just print this solution. So here we can just print the solution. To do this, it is enough to traverse the solution vector. So here we just type solution. And now we traverse all of the elements of this sequence. So from I is equal to 0 until I is less than n. And we traverse all of the elements. And so here we can print the value of all of the elements in this sequence. So we here print the value at position I of this solution vector, and we print a space and an empty space to separate the elements. So at the end we can print an end of line. Now formally here, okay, we only want to print space blanks between elements. So in the last element we really don't need to place a blank space. We don't need that. So in fact, we can normalize this. Okay, this is normally done, although this is not mandatory. It is not going to be seen in the presentation, although this is more formal. So we check if we are not the last element. So if the value of I is not n minus 1, if we are not the last element in the sequence, we print a space after each element. Otherwise, we don't print any space. So else, if we are the last element, we only print the element, because at the end we know that we are going to print an end of line. We are going to print a line break in here, right? So this is more formal to have it done like this, although both cases can be presented as the display of the solution. Okay, so with this we're ready to execute this program. We can do it from debug, start debugging, F5 or just local Windows debugger. Let's press local Windows debugger. And also before pressing the run button, okay, we check all of the code is right. Also here the increment is with ++. With this we increment the value of I at each iteration of the hill climbing main loop. Very important, otherwise we are going to have an infinite loop, right? So it seems everything of the code is fine, so we can just press the run button. Here we can see the solution that we obtain. This solution represents a valid solution to the n queens problem with a board size of 8 by 8. Remember, each number corresponds to the row position of a queen in each column of the chessboard. We can visualize this solution very easily. Here we can see how in the first column of all, the column 0, the queen is placed at index 3, so 0, 1, 2, 3, this is true. At the column with index 1, which is this second column, the queen is placed with the row index 5, so 0, 1, 2, 3, 4, 5. And this is true for all of the remaining queens. And as we can see in this solution, there are no queens threatening each other, which means that no two queens share the same row, column, or diagonal. Of course, in the hill climbing algorithm, as we keep executing this algorithm several times, the solutions that we are going to get are going to be different, but all of them are going to be the optimal that hill climbing has found with this amount of iterations. We execute again, we see another solution, we execute again, and we see different solutions. Very well, with this we end the solution of this problem on implementing hill climbing for this constraint satisfaction problem, the n queens problem. We remind the student that you can download all of this code and all of the implementation, as well as the documentation on the downloadable documents of this lecture.